So imagine we're standing right on the edge of a total technological revolution. We've got the blueprints for quantum computers that can solve completely impossible problems, quantum sensors with unimaginable precision, and a perfectly secure quantum internet. But there's a massive traffic jam on the quantum highway. What is the fundamental physical limit, the biggest bottleneck holding back the future of all this quantum technology? Well, it turns out that getting the fundamental building blocks, entangled particles, to generate efficiently is incredibly difficult. Welcome back to The Explainer. Today, we are decoding some seriously cool research titled Automated Experimental Design for High Probability Entanglement Generation. This paper introduces a brilliant automated algorithmic approach that doesn't just improve quantum experiments, it completely challenges the historical rulebooks of how physicists even think about entanglement. Here is our roadmap for today. We're going to hit 5 key stops. First, the quantum entanglement bottleneck. Second, a hidden quantum trade-off. Third, the automated design solution. Fourth, breaking previous performance baselines. And finally, a brand new quantum paradigm. All right, let's jump right into part 1, the quantum entanglement bottleneck and the big generation challenge. You probably already know that entanglement is the absolute lifeblood of quantum computing, sensing, and communications. And out of all the hardware platforms out there, photonics, using particles of light, is incredibly promising. Photons can travel super long distances with very low decoherence, and we can utilize mature tech we already have, like optical fibers and integrated circuits. But to actually get these entangled photons, experiments rely on probabilistic sources, usually something called spontaneous parametric downconversion, or SPDC crystals. And you know that word, probabilistic? Yeah, that's exactly where our headache begins. Because generating these entangled photons is highly probabilistic, it's incredibly slow, and honestly, it creates a massive bottleneck. When you blast these SPDC crystals with a laser pump, you don't just get perfect entangled photons handed to you on demand. You actually have to read for very specific detector click patterns to line up perfectly. It's literally like waiting for lightning to strike exactly where you want it. Agonizingly slow. Which brings us to section 2, the hidden quantum trade-off, specifically fidelity versus probability. So historically, physicists have played it super safe by operating in what's known as the low-gain regime. Basically, this is an experimental setup where the laser pump is kept intentionally weak. Why do they do that? Well, if you pump it too hard, the crystal might actually spit out multiple pairs of photons at once. And for a long time, those extra photons were just considered noise, stuff that messes up the quality or the fidelity of the entanglement. So, to guarantee high fidelity, physicists massively sacrifice quantity. This was the old rulebook. It relied on that low-gain regime, simplifying the math by just pretending those multi-pair photon events didn't even happen. It completely ignored the huge trade-off with success probability and left us with extremely low success rates. But the researchers behind today's paper wrote a new rulebook. They push way beyond the low-gain regime by explicitly optimizing the fidelity probability trade-off and, get this, actually embracing those higher-order emissions. They managed to massively increase the counts per second. To really visualize this trade-off, take a look at the graph right here. See that purple curve just absolutely plummeting? That shows the massive drop-off in counts per second as you push fidelity closer and closer to 100%. The traditional low-gain regime is camped out way down at the bottom right, literally at the bottom of the cliff. Sure, they get near perfect fidelity, but the success probability is basically zero. The researchers argue that this entire massive spectrum of higher counts per second has just been totally ignored by the old approximations. So, how do we fix this? Let's move to section 3, the automated design solution, using AI for quantum setups. Manually solving this physics trade-off is mathematically daunting, so the team built an algorithm that does it in 4 structured steps. Step 1, it does a broad search across target fidelities by just randomly shuffling the physical sorting of the laser sources. Step 2, it takes the best candidates and simplifies them, pruning away the dead weight. Step 3 is a local search, tweaking and re-optimizing those solutions. And finally, step 4, it outputs the absolute best-performing experimental designs ready for the lab. And you can see the algorithm's success right here on this plot, which maps the Pareto front. Basically, that's the absolute optimal boundary between fidelity on the x-axis and success probability on the y-axis. The open red circles are the broad search. The green dots are the simplified candidates, and that solid purple line right at the very top edge, that is step 4. Those are the absolute best designs discovered by the algorithm. It found this beautiful mathematical sweet spot that human intuition just couldn't pinpoint. So why does this work so well? Well, it systematically sweeps target fidelities from 75% all the way up to 99%. But its real secret weapon is that it treats the physical ordering of the SPDC crystals as a discrete search variable, while jointly searching continuous parameters like the squeezing phases and factors. In the old low-gain regime, physicists just assumed the physical order of the sources didn't matter. They assumed the sources commuted. By throwing that assumption out the window, the algorithm unlocked entirely new experimental topologies. All right, time for the moment of truth. Section 4, breaking previous performance baselines. Just look at these results. Across all three of these charts, the algorithm's new proposals are the green dotted lines, and the best human-designed baselines are the solid purple lines. Whether we are looking at the W state, the heralded bell state, or the NOON states, those green dotted lines are absolutely crushing the purple ones. The algorithm isn't just keeping up with human logic, it's vastly outperforming it, delivering orders of magnitude more expected counts per second. Just for a quick refresher on what these states are doing, the 4-qubit W state is super robust against photon loss, and the algorithm used clever destructive interference to generate it more efficiently. The heralded bell state is your classic, famous form of entanglement, and here the algorithm optimized an 8-mode setup to replace older linear optics. And the NOON states, which are used in super precise metrology, entangle the actual number of photons using ancillary or helper optical paths. In every single test case, the automated design took the win. But the story actually gets crazier. Let's head into our final section, a new quantum paradigm, and a genuinely shocking discovery. Here is the twist. You know those higher-order multi-photon events? The extra photons spitting out of the crystals that the entire physics community thought were just annoying noise? It turns out they actually benefit experimental performance. Yeah, you heard that right. The exact thing physicists were actively trying to suppress in the low-gain regime turned out to be a massive resource when the algorithm figured out how to harness it. To really grasp this, check out this graph showing the relative contribution of those high-order multi-pair emissions, the noise, to the overall fidelity. Look at that top blue line for the n equals 4 n0 n state. At 90% fidelity, over a fifth of the total fidelity is coming directly from these high photon number emissions in the ancillary paths. That is huge. The researchers hit the nail on the head with this quote. Interestingly, we see that higher-order events can enhance the experiment's performance when using ancillary photons. By simply stepping outside the comfortable box of traditional human assumptions and letting the AI explore the messy, complex math, what we thought was a bug was transformed into a brilliant quantum feature. And that leaves us looking at a completely new frontier. As we wrap up this explainer, I want to leave you with this to chew on. What other major scientific roadblocks could be totally shattered just by letting automated algorithms challenge our basic assumptions? If an AI can look at quantum noise and see a vital resource, just imagine what it might uncover in chemistry or material science or medicine. Keep questioning the rulebook, everyone, and thanks for joining me.